Hello everyone and welcome. Thank you for joining us this morning for the third in this series of webinars looking at smart grids and timing and synchronization for smart grids. Today the title is Converging the Energy Grids of Tomorrow. So a quick recap. The concept of a smart grid is moving from our traditional energy generation and distribution model. Over the years, we had a few large centers of generation, fixed distribution in one direction, passive consumers only taking part in using energy and paying. Now we're moving to more of a bi-directional flow of both energy and data, diversification of energy sources, lots more smaller generation sources, local and micro generation, much more dynamic and reactive energy grid than before, and we're seeing smart cells, brokers and agents within the grid looking at buying and selling energy with autonomous computer or artificial intelligence controlled connection and disconnection, looking at the wholesale energy market and connecting and disconnecting load and generation at the same time, and a whole focus on decarbonisation of the transport infrastructure, moving towards more electric vehicles that's creating challenges for the grid as it was moving forwards to a smart grid. In terms of timing and synchronization, where do we need it? Well, as before with the generation, we need to make sure that with the power we generate, the voltage is in phase with the grid as a whole. So synchro phasers will measure that down to accuracies better than a microsecond. Current and voltage are sampled and measured across the whole grid. Sampled values are used. The digitalization of substations that is talked about in the IEC 61850 standard, sometimes called the digital substation, calls for the precision time protocol, PTP, a timing standard, a timing over network standard, also known as IEEE 1588. And lots of generation and grid tie systems require synchronization to the grid for generating voltage that's in phase with the grid. And also for metering as well, we need time, traceable, in some cases legally verifiable and traceable time for metering systems, and for these smart broker agents that I talked about earlier. And in this grid, we're moving from, as I said, fixed places of generation to more DC sources like batteries, energy storage sources, for example, EVs, electric vehicles that may be able to put energy back into the grid if needed. So all of these things, all of this more complex control of the energy grid requires time synchronization and requires a single timescale to be in use across the whole grid, which is usually traceable to UTC, universal time, that we usually get from satellite navigation services like GPS, that their timescales are traceable back to UTC. So a quick recap there on what we mean when we talk about the smart grid. The focus of this session today is about convergence. And it's really about the convergence of these two different disciplines, two separate disciplines that exist within a power utility company. So a distribution company, typically, we have the telecom and the protection. So in inverted commas, protection, also sometimes known as power engineers, real-time SCADA, the power, the high voltage, the voltage distribution, the energy portion of the utility company, as separate from the communications portion, the so-called telecom portion. So telecommunications engineering, telecommunications is really transportation of data, connection of different devices, exchanging data between them, whether they're connected locally via a short cable or whether they're connected at opposite ends of the country and there's some sort of telecommunication network between them. Interestingly, this definition I found talks about telecommunications engineering being a combination of both electrical engineering and computer science. And the protection, the power engineering, the power engineers, a very high level description of that is that power systems engineering, it's a subset of electrical engineering. So they have that in common. These two disciplines, telecom and protection, have the electrical engineering part in common, but they are often very different different parts of a business that perform these functions. Indeed, in some cases, they're often either different business units or different companies. In some cases, the telecom infrastructure within a power utility is outsourced to a completely different company who runs the telecom, the communication links to provide some of the necessary functions to the power, to the protection side of the business. So in general terms, telecom provide backhaul, general connectivity for remote sites. And obviously the power grid as it is has to cover almost all of the population. So in really rural, remote areas, we have power energy distribution assets that we need to connect our telecom network to for the monitoring and control, alarm and status and data collection. All those functions are enabled by the telecom part of the network. So the remote data that's needed to control and maintain and run the power distribution network is enabled by the telecom part of the business. So typically the protection, the power engine would be interested in measuring, monitoring and controlling the energy flow, disconnecting and connecting distribution assets depending on local status, local data or remote data, and making sure that things are safe, things that operate efficiently. But often these two parts of the business are often in cases where with critical national infrastructure, if something goes wrong, if the power grid fails due to weather, as we've seen recently, and because these are two different parts of the same business, or in some cases two different companies, there can be some sort of blame going on between them, some sort of, the relationship is not the best between these two parts of the business. But for the smart grid, these two functions are having to converge together. They've been through their own types of convergence in the past. So again, they share things in common, these two different portions of the business. The telecom networks have over the years, over the decades, changed from electromechanical, manually switched to solid state, circuit switched, and now to Ethernet. So telecom networks are all converging on basically packet switched Ethernet type networks. And the same is happening in the protection, in the power side of the business as well. Typically, dedicated hardware interfaces that might be circuit-like or direct connections are now moving onto Ethernet networks. So this IEC 61850 standard I referred to is calling for use of Ethernet within substations. So the convergence is happening within these two silos, within these two parts of the business. So they share that in common. And for smart grids, proposing that we should converge these two functions together to maximize efficiency and to maximize the benefits of the technologies that both of these sides of the power utility business provide. So the smart grid requires more convergence, that thing about computer science, adding the intelligence into the grid, adding the measurement, the monitoring, the control of the grid under increasingly autonomous circumstances. This evolution that we're seeing towards smart grids is adding the intelligence into the functions that manage the energy and the data flows within the grid because of microgeneration, because of bidirectional flow of both energy and data. And so we're combining some techniques and philosophies from telecom engineering with traditional and new power management strategies. And that's what is driving the smart grid, what is enabling the smart grid to do the smart things that it can do. So if we have a look at an overall network, timing network for what a smart grid might look like, we can see we've got GNSS, so global navigation satellite systems. Typically GPS is the most common one of those, the European Galileo, or the Russian GLONASS or the Chinese Beidou systems, the four main constellations that we generically call GNSS. They give us UTC traceable time. We're seeing now more and more awareness of security and cybersecurity vulnerabilities in these networks. So operators are bringing that timescale under their own control by using their own local atomic clocks like cesium. When the GNSS signal is good, they are looking at effectively steering these local cesium clocks towards UTC. so that if any interference occurs with that satellite signal, then our local timescale that's owned by the operator, by the power distribution company, the power utility company, that can hold accuracy to UTC for less than 100 nanoseconds for many weeks. So we have this concept of this enhanced primary reference time clock that gives us a clock reference for the whole network, not just the telecom network. You'll notice here on this slide, there's no demarcation between telecom and protection. We are looking at timing particularly, and within the substation, so right at the bottom of the slide, the digital substation clocks are using Ethernet networks within the substation. So these clocks themselves are can be traceable to UTC. I know that lots of applications, lots of measurement and monitoring applications don't need absolute time within the substation. They only need to make sure that there's a time based, so they can make relative measurements within the substation. But great efficiencies can be achieved if we can have the whole network using the same time reference. And that gives us greater visibility as well for things like fault reporting and event logging, working out exactly what happened when, if we have the same time base, a unified time base across the whole network, which we can achieve if we converge our telecom and our substation networks in this way. So to look at that in a little bit more detail, what we're proposing is, what we're saying with this idea of convergence between the telecom and the protection worlds, is we deliver our accurate traceable time. We deliver a source of accurate traceable time from our core telecom network. So on the left-hand side of the slide, we have synchronous Ethernet and PTP, the precision time protocol, available from our core network. Our core network will probably be using a GNSS receiver somewhere and a backup atomic clock. So we will have GNSS and probably a cesium clock somewhere. Our local substation, which is the middle portion and the right-hand side of this slide, is designated by these clock entities, these functional entities, where we do still have local satellite time receivers. So we can get local time from satellite receivers if for whatever reason our reference clock in the network, if there's an issue with it or our network link fails, we still have a local source of clock, source of time. We're using a GNSS firewall, which looks much more in depth into the signal, into the data within those satellite signals, to make sure that they're not spoofed signals, to make sure it's not an attacker, a cyber attacker, trying to steer the time in our substation away from where it should be to try and cause faults. And then we have some sort of reference clocks within our substation where we can we're showing in the middle and on the bottom side here, two separate clocks, but we could have one box doing both of these functions, delivering both NTP, the network time protocol, for any workstation or any other service or client within the substation that requires time for timestamping of events. For the very high precision applications that need a microsecond or better of error, then IEEE 1588 or PTP, the precision time protocol, is what we typically use. So we have this concept of then delivering those within the substation to the applications that need them. We have local access to satellite time services, but if we need it, we can get a backup from the network. Or if we want to ensure that our local time is the right one, we can compare it with another source from our network. So again, the idea is converging the supply of time, the utility of time from the telecom portion of the network with the users of time and the time delivery mechanisms that are within the substation itself. The second webinar in this series focused very specifically on cybersecurity. It's still available on demand to watch. But substations typically, in some cases, do have antenna farms as well, where we'll have multiple racks within a substation, will be assembled by system integrators, and they will include, each rack will typically include its own time reference. And typically they could be different manufacturers, different modules of GNSS receivers. So we end up with, in just one substation, for example, something like 8 or 10 separate satellite antennas. So obviously with a GNSS firewall, we can use one outside antenna with the in-depth signal analysis that can look for spoofing and jamming events, then that can provide that signal through a splitter to all of the timing receivers that might be in all of these racks. In terms of thinking about convergence again, converging the timing networks together, the telecom networks themselves have been through an evolution where typically today we see this type of architecture on the left-hand side, where we have indeed the top layer and the middle layer on the left-hand side of this slide merged together. So our reference clocks, our primary reference clocks, merge into our optical backbone. So the middle layer on the left is our backbone network, which typically today is DWDM with Ethernet over DWDM, which is slowly being rolled out to replace in the power industry the old teleprotection circuits that use E1s and PDH, SDH applications. So our backbone optical Ethernet DWDM layer can provide very high accuracy, very stable, very resilient and traceable time to any regional layers on the bottom layer on the left-hand side of the slide, where we might still have PDH and SDH islands. We might still have PDH and SDH equipment that requires synchronization, requires a frequency source to provide those E1 sort of old SDH, PDH teleprotection applications. But the newer technologies, GNSS, synchronous Ethernet and PTP, give us the opportunity to get highly accurate time into almost all parts of the smart grid. And the idea is that we converge the clock and the network together, so the network becomes the clock. This concept is known as the virtual primary reference time clock. So the PRTC acronym is primary reference time clock. The ePRTC, the enhanced primary reference time clock, is the version that has a local cesium, a local atomic clock with it, to give us the very, very good holdover, the very accurate phase holdover performance that we would need if we had a prolonged outage of our satellite time reference. The little yellow box to the top right is the ITU standard that defines the enhanced primary reference time clock. This concept, the virtual primary reference time clock, is when we put all those together on an optical network that we link together with these boxes at each nodes are known as high performance boundary clocks. So this HPBC, this is an optical DWDM network. These high performance boundary clocks are linked together with direct fiber connections, usually with bidirectional SFPs or bi-die SFPs, so a single fiber to manage the asymmetry. And we can use these high performance boundary clocks to get time around this optical network ring to within 5 nanoseconds. So the error from any of the reference clocks to any of these boundary clocks is better than 5 nanoseconds. Now we have our local timescale generation, which includes our satellite clock, our cesium clock for holdover, our GNSS firewall to look at to assess the quality of the satellite reference, and again our time unit that interfaces into the optical ring. This particular example, this particular slide here shows this local timescale generation at each of the 4 regions. You wouldn't necessarily deploy them at each of the 4 regions. You wouldn't have to. You'd maybe just deploy them in 2 regions for resilience. But the idea is that with this type of optical backbone connection, we can get very accurate time around the whole optical network. So wherever the protection applications are, as long as they have connections to the backbone network, then we can drop down from these high performance boundary clocks. We can use PTP and or synchronous Ethernet to get very accurate time into those applications. So the digital substation clock that's providing PTP using a different profile, using one of the power profiles into either the process bus or the substation bus within the digital substation, can use as its reference this very highly accurate clock reference from our virtual PRTC network, where the network becomes the clock. It's virtual because wherever you are on this network, you can get access to timing that meets this enhanced primary reference time clock standard. So the network effectively becomes the clock. The clock lives within the network. Doesn't really matter where you are. So to summarize, converging the energy grids of tomorrow. Fundamentally, we know that smart energy grids require time synchronization. I think as more and more smart applications or even smarter applications arrive in the smart grid, some of these automated agents that are buying and selling energy depending on the wholesale price and depending on supply and demand, all of these type of applications are only going to increase the requirements for not just for time synchronization, but for the accuracy of time synchronization. The network evolutions that we're seeing, the technology progression that is happening, where we are now deploying using these optical DWDM backbone networks, utilizing high performance PTP boundary clocks, we know that we can get time around these optical networks to within 5 nanoseconds of error to the boundary clocks. Typically any other point, any other PTP point below those high performance boundary clocks, typically we would say much better than 100 nanoseconds of error to UTC. And if there is a solar storm, if there's some sort of event that knocks out the satellites themselves, knocks out one constellation or more constellations, then we know our cesium in our network will give us weeks worth of holdover before we run into problems. So secure, resilient, and traceable time is now being able to be delivered to more and more points within this smart grid. Obviously, it improves the efficiency, better monitoring and control, and enables these smart grid features. And it really depends on the convergence. So converging the energy grids is really focusing on the telecom, the protection networks, the timing parts of those networks, joining together and utilizing the available technology to increase resilience and increase performance. And these new virtual primary reference time clock architectures provide local traceable time anywhere in the network. Okay, that's the end of the slides. Thank you for joining us today. Just let me have a look and see if we have any questions that came in while I was speaking. Just bear with me. Okay, so I have one question here from Steve. He asks, will an end user producing power and sending to the grid also need a source of timing? So thank you for this question, Steve. I think typically if you're a consumer, if you're an end user, then the synchronization with the grid in terms of voltage, the phase of the voltage will be handled by the equipment. It will probably be the timing requirements for an end user, for a consumer, will probably be around billing and your meter, your smart meter, measuring when you delivered and how much power you delivered into the grid. So I'm sure there will be a requirement for end users to be synchronized, to have an accurate time reference. I don't think it will be the same levels of accuracy that I was talking about in some of the slides. It'll probably be half a second or 100 milliseconds or more in terms of billing, in terms of measuring. Yeah, I hope that answers your question. So I think that's all the questions we had today. Thank you for joining us. Our next webinar series will be looking at timing in financial services. If you have any colleagues or if you're interested in financial services timing, then keep an eye on our social channels and keep an eye on our website where we will be publishing details of that. So thank you very much for joining us today.